please give a warm welcome for our last talk today, Harrison and Ian will talk about pulling the MikroTik into the Limelight.
All right, hi everyone. Welcome to our talk. This is pulling MikroTik into the Limelight, demystifying and jailbreaking RouterOS. So I'm Harrison. I'm a security researcher at Margin Research, and I also do reverse engineering for the Dice Gang CTF team, and I'll be starting a PhD in the fall.
Good afternoon, everyone. I'm Ian DuPont, also a security researcher at Margin Research, focused mainly on IoT and embedded devices. So as the name of our talk suggests, today we're going to be talking about knowledge that Harrison and I have gained and tools that we've developed reverse engineering MikroTik routers over the past handful of months. If you're not familiar with MikroTik routers, they can be a particularly difficult target to get into. As opposed to other routers, which may run more like a collection of independent binaries, MikroTik is very much a system-wide implementation. And there's not a ton of information available publicly about how that system-wide implementation works. In fact, MikroTik prefers to live more in obscurity, and the information that is available happens to be a couple years old now. So the purpose of this talk will really be to refresh that public information. And we're going to do that in four ways here. So first, we're going to take a deep dive into RouterOS internals. We'll show how processes boot, how firmware is cryptographically signed, and how you can bypass that signature to get a developer shell on the virtual machine image that MikroTik maintains. Next, we'll talk about something that's really fundamental to MikroTik, which is their internal messaging process for IPC. As I said, this is a system-wide implementation. There's a lot of sharing back and forth of information between processes. So we'll explain what that looks like and how it works. Third, we'll talk about MikroTik's authentication and go over a novel implementation of hand-rolled cryptography that magically works. And then the talk will culminate in the release of a novel jailbreak, the first of its kind in over 3 years. Harrison will walk us through the vulnerabilities that make this possible and show you how you can get a shell on any version 6 RouterOS firmware. So the goal overall of this talk is a crash course to take you from potentially zero knowledge of MikroTik systems to a point where you can feel comfortable recognizing key aspects of the firmware, and then share with you tools that we've created to really accelerate your reverse engineering, tool development, tinkering, whatever you're interested in. So if you are someone that has zero knowledge of MikroTik and its routers, we would be remiss if we didn't at least do a high-level overview. So MikroTik is a Latvian router and switch company. They write their own firmware, manufacture their own devices. These devices are released with multiple architectures, so you can choose whichever you're most comfortable with reversing. Really, the most important thing and differentiator for MikroTik routers is the fact that they run a standardized operating system. So anyone who's done router reversing probably knows that it's not uncommon to take two routers from the same manufacturer that are comparable in quality, to open them up and see that they run services in completely different manners. That's not going to be the case with MikroTik. Every one of MikroTik's routers runs RouterOS, and all RouterOS releases are backwards compatible, which is nice for us from a reversing standpoint because anything that we find is immediately applicable to all RouterOS devices. And then MikroTik also standardizes this UI, extends their standardization to their UI, which is really nice from a user perspective. So here we have a RouterOS shell that gives us configuration options. If we prefer a GUI, this is the Winbox executable that MikroTik releases and maintains, just connects on a different port, and it gives you a GUI interface for the exact same configuration options. And if we take a look at the web configuration portal, WebFig, again, identical. So you only have to learn one configuration scheme for all of your MikroTik devices. Now that makes MikroTik a good product, but what makes it a compelling target to research? So this is a Shodan dump from a couple weeks ago showing over 3 million devices worldwide. And you see here that, of course, everything is running RouterOS. So this is a potential vulnerability because you can take CVEs, say a handful of end days like TrickBot did, and create a botnet of MikroTik devices that are unpatched. And they use this as a proxy between their infected devices and their C2 servers. You can extrapolate that and consider what happens if we find an O-day on these devices. Theoretically, it could be applicable to all 3 million MikroTik routers worldwide. So it behooves us as researchers to take a look, make sure the security is as strong as it can be. So That's what we're working with. Now that we know, we can dive into how it actually works.
All right, so let's dive into RouterOS. So there's two main versions of RouterOS that are currently in use. So version 6 has been in use for many years now, and it's like the long-term support version. It runs a pretty outdated Linux kernel and a very outdated standard library. Version 7 was released just a few months ago. It was a pretty major upgrade, so they changed kernel versions, and they changed standard libraries, but they chose a really old one anyways, which is interesting. So a lot of the content in this talk applies to both version 6 and version 7, and we'll try to point out any differences. Most of the screenshots we show are from version 6, so the struct offsets and vtables might be slightly different in version 7, but it's all the same idea. So one of the cool things about RouterOS is that it runs on like a whole bunch of architectures. So for whatever reason, MikroTik decided to build devices in like every architecture they could. So it runs on 32 and 64-bit ARM, PPC, MIPS. It runs on x86, and it even runs on this tile architecture, which I'd never heard of, but apparently is a thing. And MikroTik also, they have standard libraries, but they re-implement a lot of their own functionality in these libumessage or libubox standard libraries. So they have their own internal library set that the processes all use. So libumessage is probably the most important of these. It manages inter-process communication and process lifecycle management. There's also libubox for some configuration abstractions, and so on. There's probably about 15 of these total. So one of the nice things from a reverser perspective about MikroTik is that RouterOS firmware is all available to download, and it's all unencrypted. So you don't have to get a device and get the firmware off of it. You can just go on their webpage and download it. So that's pretty nice. So all of the software for RouterOS is contained in these packages, these NPK files, which we think stands for Nova package. And the format is pretty standard. It's been described before. Essentially, an NPK file contains a lot of these blobs. Each blob has a tag, which is like an identifier, a size, and some data. In previous RouterOS versions, there used to be things like install scripts and update scripts, but those have been mostly replaced just by a single squashfs that contains all of the package data. One thing to note, though, is that packages are signed. So all of the packages have a signature that's verified when you install the package and also every time you boot the router. So it's difficult to sort of install your own packages as a researcher. This is sort of what the file system looks like in an overview. So the only writable region of the file system is flash read-write. And this contains folders like disk, which is where you can store user-uploaded files. It also contains the logs, temporary directory, etc. Those core RouterOS libraries that I mentioned are in /lib, and then the core system package gets installed into /nova, either bin, lib, or etc. And then each additional package that you install gets installed in a separate /package/name/nova namespace. And there are a lot of processes in MikroTik, which makes it a pretty interesting target. So a lot of these binaries implement like one specific function. For example, user is the binary that's responsible for doing authentication. And any process that needs to do user authentication will start sending messages to user in order to sort of do like remote procedure calls to do authentication. So from a security perspective, this is pretty nice because you just have to get authentication right once, and then all of the binaries that call into user will use the same functionality. So it's sort of a single point of failure in that sense. So unfortunately, MikroTik RouterOS is locked down. So you don't actually get a shell. You get sort of a restricted shell that gives you configuration options. So you don't have access to the underlying Linux system. However, there is this developer backdoor that's existed for a long time, and it's pretty well known about. So basically, if you can log in as the user devil and you have some option package installed, it will run bash for you instead of the restricted shell. The main problem is that this option package doesn't exist. It's presumably just something internal to MikroTik. And additionally, since packages are signed, we can't easily just create an option package and install it ourselves. So one thing we can look at is how to disable this signature validation. So here's an overview of what the disk image for RouterOS looks like. This is version 6, but it's pretty similar for version 7, just the offsets are a bit different. So basically, there's two partitions. There's a boot partition, which is the first thing gets loaded, and there's a main partition. So inside the boot partition, you have the kernel image, and you also have this init rd.rgz, which contains this init binary. The init binary is the first thing that runs after the kernel, and it's responsible for loading all the packages, mounting the file system, and doing signature validation. Packages you install get installed into the main partition, and basically the whole package image is just stored in a single file, and it reparses it during each boot. So how can we patch out signature validation? Well, if we look in the init file, there's actually this nice function that does presumably check signature. If you're interested, you can find it by just grepping for that string. And all we need to do is just patch this to return true, and it will just say every package is valid even if the signature is not. So that's handy. However, we run into a problem. So how do we actually take this patched init file and replace it in our compressed init.rd RGZ? And specifically, there are a few problems. So the kernel makes some assumptions about where this file is in memory. Basically, when you compile the kernel, it knows that information, but if we change it, it gets confused. So we need to match a few things. One, we need to match the decompressed size of our directory, which is easy enough. Then we need to match the actual compressed size of our init.rd.rgz. And finally, we need to actually match the position in the boot image where we store this file. So if you just try to mount the boot image as a file system, for example, and copy it in, it'll just rearrange things and the kernel will get confused. But we can solve these problems. So the first thing we do to match the compressed size and the decompressed size is we can use this entropy trick. So the idea is we'll create this pad file in our init.rd directory and increase the size until our decompressed size matches. Then what we can do is basically change the amount of entropy in our pad file to adjust the compressed size that we'll get. And specifically, if we have low entropy, like a lot of zeros, our compressed size for init.rd.rgz will be very small. And if we include a lot of random bytes, the compressed size will be bigger. So as long as our target compressed size is somewhere in between, we can do like a binary search, and it perfectly matches the compressed size. Then once we have our new init.rd.rgz, all we need to do is just find and replace all of the individual sectors in the disk image. So rather than mounting as a file system, we'll just literally replace the actual bytes in the disk image. And that's pretty much all we need to get a shell. So now that we've patched out signature validation, we can just construct an option NPK with bin bash and bin busybox. Importantly, the signature doesn't have to be valid because we've just patched out signature validation. And once we reboot the router with this package, we can telnet as devil, and it will give us bash, and then we can just run our busybox shell, and we have a much nicer reversing environment. So this technique works on pretty much every version of RouterOS, and it gives you sort of a persistent backdoor, which is useful for research purposes. Cool, so now we're gonna get a little bit more into the weeds and talk about MikroTik inter-process communication, which is pretty crazy and a little bit seems to be inspired from TCP/IP, which makes sense for network developers, I guess. So the main player in this IPC is this Nova message object. So this has been described before in a few previous RouterOS talks, and essentially it's just a typed key value mapping. So there's a few different types: unsigned 32, unsigned 64, Boolean, string, bytes. You can store IP addresses, and you can have recursive Nova messages. There's two variants of this. So on the left, we see their sort of pseudo JSON variant. This is now deprecated, so RouterOS doesn't really use this anymore. And on the right, we see the serialized binary version. So this is what's in use across RouterOS nowadays. And it's not too complicated. We made like a little cheat sheet here. There we go. It might be a little hard to read. We've also tweeted this out if you want. I'm not going to get too into detail about this. It's like a pretty straightforward format. So you can implement your own decoder if you want. Cool. So keys in this message thing are 24-bit. And each key, so some keys are sort of like special keys. And the most significant byte of the key indicates like a group for namespaces. So we've shown a bunch of different namespaces here. The most important ones are hex FF, which is the sys namespace. This contains all of the keys that are used for internal message processing, and hex FE, which is the standard namespace, which contains a lot of keys that are used for things like editing values in the GUI or reading and writing values. So here are all the elements of the sys namespace. This is specific to version 6. I think version 7 has a few more. Important ones to point out are hex FF 0001 and 0002, which are sys2 and sys from. So these contain the destination and the origin for messages that are sent through the system. And also hex FF0007 contains an integer that describes what command to run, sort of like which command to do in an RPC. And there are a bunch of default commands. So here are sort of some special commands that have like default handlers. These are used, for example, if you're in the configuration panel and you're adding an IP address, it'll invoke like set object. If you're retrieving IP addresses, it'll be get object, and so on. So this is used sort of system-wide. But binaries are also free to implement their own commands with different numbers. So this is just the default list. So here's an example, what example RPC might look like in the actual code. So in this example, we have novabin www is trying to authenticate. So it's going to send an RPC message to novabin user with the username and password. And user will do some authentication processing, and then it'll reply with OK or fail. And the important things to notice here is we're setting sys2, which is hex FF0001, to 13.4, which somehow corresponds to novabin user. And additionally, we're setting hex FF0007, which is the command, to 1. So we're going to run command 1 in novabin user. After it constructs this message, it calls exchange message, which will send the message and then block until it gets a reply, and then it will proceed. So how do messages actually get routed through the system? So here we need to look at novabin loader, which is sort of the router's router. So novabin loader is the first process running after boot, and it's responsible for spawning all of the other processes, and it maintains a socket connection to them. And it's also the thing that manages message routing. So for example, in this RPC call, we have loader connected to www at address 70 and user at address 13. And I've drawn this as a network diagram because I think it's kind of funny that you have this network inside of a router. So just remember that this is all running inside of a MikroTik router. Yeah, so when we look at loader, we see that it's loading this system.x3 file. And it's reading it with libu XML++. So you would think it would be XML, but it's actually like a weird serialized thing. But when we reverse this library, we can sort of decode the format, so we get this nice specification. So this is used sort of system-wide in RouterOS, this like X3 format. I'm not exactly sure why they thought it was necessary to do this, because XML would be pretty fast anyways. But anyways, essentially the document contains root node. Each node can contain attributes and also children nodes. The attributes have a tag, which is just a 32-bit ID, a type, which can be string, Boolean, unsigned 32, or signed 32, and some value. So using this information, we can produce sort of pseudo XML for these files. So when we apply this to our system.x3, we see this nice pseudo XML file, which looks like it contains a list of all the processes. And if we look for novabin user and novabin www, we see that 13 and 70, which correspond to their RouterOS address. So that's pretty useful, but there's sort of a remaining question is we saw that it was setting sys2 to 13,4. So what does the 4 correspond to? Well, it turns out that there are these things called handlers. So processes can sort of create their own subnet by creating handlers. So in novabin user, we see a call to add handler with index 4. So that's what the 4 corresponds to. So now our network diagram expands a little bit. So under user, we have all of its handlers, one of which at index 4 appears to be some sort of login processing handler. Handlers work mainly by using vtables. So the handler has a huge vtable that implements functions for all of those default commands that I showed before. And also it can implement things like just a pure handle command, which gets invoked for any command. Inside message handling, handlers can do introspection on the message, so they can pull out fields, they can check if a message has certain fields, and then if the message was a request, they can respond to the message with reply message, or if it was an error, they can reply with an error, and so on. So this is, when you start reversing RouterOS, you see a lot of this type of code. This is the bulk of the communication. So there's sort of one more player. So every process has a Nova looper. And the looper is sort of like the main struct that's used by the process. And it performs the handshake with the loader and facilitates communication. So every looper contains a default handler. So for example, if you send a message just to a binary, not to its handler, it can handle that directly. And the looper also provides the communication abstractions like exchange message and send message. So I want to do a quick example of how messages are actually routed through the system, because it's sort of interesting. So here we have an example diagram. We have our loader binary. We have two processes running, foo and bar, at address 12 and 34. And bar has a handler at address 50 called sub. So in this example, foo is going to send a message to bar/sub. So we start. Foo basically creates a message with sys2 set to the destination, in this case 34,50, and initially sysfrom is empty. And foo will basically send this through its looper to the loader binary. The loader binary will check which socket it's receiving this on. It figures out it's from foo, so it will append 12 to the sysfrom entry, indicating that it's from foo, and it will figure out what's the target binary. In this case, 34 is the target binary, so it will strip that from sys2 and forward the message to bar. So when bar receives this, it sees sys2 is 50 now, and sysfrom is 12. And since sys2 is not empty, it needs to forward it again to its own internal subnet. So it will look for something beneath it that has address 50. In this case, it has a handler at address 50, so it will strip that value and forward the message to the handler. Now the handler can process it. For example, if it's authentication, it can do something like that. And when it wants to reply, all it needs to do is flip these arguments. So sys2 is now 12, which corresponds to foo, and sysfrom is empty, and it will propagate it back up the stack. When bar receives this, it will figure out which handler it's coming from and append the corresponding sysfrom entry, in this case 50, and then it will forward it back to the loader. The loader will append 34 for bar and strip off the 12 for foo, and foo receives this message. So this protocol is pretty interesting because one nice feature is that it protects against sysfrom forgery. So when messages are being sent through the system, the sysfrom entry is initially empty, and it gets appended every time it goes up in the stack. So the parent of whatever the object is always assigning sysfrom. Additionally, this means handlers are sort of namespace independent, which in theory means they could be refactored easily. Finally, if you try to send a message to a binary that's not running, loader can recognize this, and it will spawn the binary before sending the message. And this is pretty nice because it means that RouterOS can shut down a lot of services that aren't required all the time. For example, Nova bin user gets shut down pretty early, and it only gets spawned again whenever you try to authenticate. There are a few more abstractions you might see if you do reversing. So one abstraction is this AMAP handler. This is a handler you can implement, and you pass it a path to like a configuration file, and it will implement a bunch of default handlers for setting and getting values. So for example, if you want to set up a handler that allows you to set, reset, and modify an IP address, you can just use an AMAP, and it removes all of that boilerplate code for you. Additionally, if you have any binaries that do user management, for example, the HTTP binary allows you to log in. Similarly, Telnet allows you to log in. They will use these Nova allocator handlers to create new addresses for users as you log in. So if multiple users log in, they'll both have unique paths in this RouterOS namespace. But what if you want to talk to several people? So the example I showed before was one binary to one other binary. But it turns out RouterOS also has multicast. So if you set sys2 to the special hex FE002, you can then give it a list of handlers you want to forward to, which is pretty interesting. So in this case, Alice is sending a message to 4913, which is Bob/foo, and it's also sending a message to Charlie. But what if you want to talk to everyone? So as you might expect, there's also a broadcast address. So if you set sys2 to this special value, it will just forward the message to every other binary. And the only place we've seen this being used is when a user disconnects from a session, it'll broadcast a disconnect message to all of the other binaries, indicating that this user has deauthenticated. So with this information, we sort of realized that all of the internal messages are being routed through this loader binary. So if we want to visualize sort of what this flow looks like, all we need to do is trace this one point in loader binary, and we sort of have access to all these messages flying back and forth. So we wrote this RouterOS message tracer tool that runs on the device, hooks into loader, and then proxies all of these messages and forwards them to a graphical front end, which lets us visualize them. So we have a quick example of that running here. So you see it running in the background. It's all the messages are coming in. And here we're logging into the web interface, and you see a bunch of messages fly back and forth. We change tabs. There's more communication happening. There's actually a surprising amount of just persistent communication that happens in RouterOS. In the bottom left, you see that the net binary is sending messages about once a second. And there's a lot of other binaries that send messages every 5 seconds or every minute, et cetera. So with this tool, we can sort of page through, look at all of the raw messages. It also pulls out like those specific sys keywords that I showed before. So this was sort of a useful tool for finding interesting communication in RouterOS for us. Cool. And I'm going to pass it back to Ian for authentication.
All right, so now we're moving into, I'm sure, what everyone has been waiting for, talking about authentication and MikroTik cryptography. So if you're one of those people whose eyes are starting to glaze over at the thought of cryptographic protocols, I just ask that you give this a shot. This is a novel implementation of some hand-rolled crypto that I don't think you're going to see anywhere else. So hypothetically, to start, if we're creating a service that requires authentication and we need to do some sort of encryption, what would we do to share secrets? And an easy and totally viable answer is use something like elliptic curve Diffie-Hellman, which is tried and true. And this is actually what the www binary that's listening on port 80 does. It has a server and a client, or Alice and Bob for more generality, that have their own private keys, A and B, respectively. You multiply your private key times G, which is a generator point with known strong cryptographic properties on the curve, and then all these calculations are taken modulus some large prime P to create a trapdoor function. Now, all of a sudden, we have a value that even if you intercept A times G and you know G, you can't back calculate A. Meanwhile, both sides are able to progress and share their secret by multiplying their private key times the value that was transmitted over the wire. So this is exactly what www does. Elliptic curve Diffie-Hellman over standard curve 25519 generates a shared secret. Shared secret initializes RC4 transfer and receive keys. So that all sounds really good. One would expect then that this is the same process that's used on other services on MikroTik. However, if we just blindly throw elliptic curve Diffie-Hellman at, say, mproxy, which is listening for Winbox traffic, that GUI I showed earlier, we fail. So we have to figure out why we fail. And what we can do is we can use tooling that we developed, say Harrison's message tracing tool that he showed just a minute ago, and intercept messages from each of these binaries to the user authentication binary. And what we find is wildly different results. You can see these long raw strings here that have long values that are presumably points or public keys, but it certainly doesn't look the same, and it certainly doesn't look like elliptic curve Diffie-Hellman, at least on the surface. So let's take a step back, work with what we have. We'll start by looking at function signatures. We see a lot of calls to the curve 25519 class. That feels comfortable. That's our Montgomery curve. We see big num and red num, reduced num, which are just vectorized representations of large integer values, and these are pretty standard for cryptographic math. Where things kind of go off the rails is this W curve class. That's presumably the Weierstrass curve, which is a different elliptic curve, as shown here with a different formula, but obviously not the same like what we saw in elliptic curve Diffie-Hellman. And then we have these other functions like red P1 and the 2-bin function of the curve 25519 class, which are doing plotting and then conversions back and forth between curves. So clearly something else is going on here that doesn't look as straightforward as we would hope. So it might be tempting to dive into each of these functions and figure out what they do. And I admit that that's exactly what I did. But what serves you better in this case is to avoid going down the rabbit hole that is cryptographic reverse math and just Google. And in a rare stroke of luck, we actually get some information from MikroTik. They publish on their wiki this statement here that Winbox uses ECSRP5 for key exchange. So that's great. If you don't know what ECSRP5 is, you're certainly not alone. What it stands for is Elliptic Curve Secure Remote Protocol, which is a specific form of secure remote protocol, and SRP is opaque. And opaque protocols are really clever ways of performing authentication during key exchange. So instead of sharing a secret, encrypting a username and password, sending that over the wire, instead what PAKEs will do is take the username and password and inject that data into the cryptographic calculation. You can imagine if we have a properly constructed protocol for this, that if both sides are using the same username and password, then both will arrive to the same shared point and the same shared secret. Whereas if you flip a byte and put in an incorrect password, that will change maybe hash values, it will certainly change point coordinates, and then you end up with a different value and the shared secret fails and authentication fails as well. So that has some really nice benefits. You never have to transmit the password over the wire, encrypted or otherwise, and you never have to store the password on the server. You could just store a hash value or something known that would perform this calculation for you. So that's all great. Again, doesn't tell us what we're looking for. We're looking to replicate this protocol to authenticate. And what we find is that if we do a lot of digging, elliptic curve secure remote protocol is much more rare than the standard SRP version, which implements RSA. So, in fact, there's very little out there that tells you anything about it, except for one particular article, which, thanks to the Wayback Machine for archiving this, is a 2001 IEEE draft submission, which, to the best of my knowledge, has not been implemented as an IEEE standard. But it's the best we've got. It looks enticing. So let's dive into it. And it's a little heavy. I'm not going to go through this because there's a lot going on here. And if we try to take this all on at once, we're going to get very confused. So let's break this down component by component, and let's start with the differences. So we notice that MikroTik, again, is using these curve 25519 classes for the Montgomery curve. That's not referenced at all in our draft. But what we can find is that it's only using these curve functions when it's converting final points back to Montgomery from Weierstrass and sending those over the wire. So let's just abstract that away, because that's a conversion that we can do. We can replicate that and focus on the core math, which is all being done over the Weierstrass curve, similar to the draft. What we find is that MikroTik is doing a lot more under-the-hood, heavy cryptographic math, and it doesn't look similar to just the straightforward functions that are defined in the draft. We can try to reverse and do our best here in Binary Ninja to get some function signatures, and again, we can be tempted to dive into this math. But again, this is heavily optimized cryptographic math that is painful to reverse engineer for decompilation or disassembly. So instead, let's back up, use tools at our disposal, say let's dump some values from these functions to see what the points look like. And what we find is z coordinates in all of the point calculations. And that's odd because we're familiar with this two-dimensional formula here that we've shown for elliptic curves. But in fact, more Googling can tell us that elliptic curves can be represented in three-dimensional space, projective space, and the z-coordinate is shown here. What MikroTik's actually doing is performing these calculations in 3D, then projecting that point down to a plane where z is equal to 1, and now we're back into our standard Weierstrass curve. So again, now that we understand what math is being done, and it's eventually getting back to this two-dimensional affine form, let's abstract away that three-dimensional equation and all the math that's being done. And now we can just focus on the core components, the core math, that is theoretically identical to what the draft shows. So let's start piece by piece again. Public key derivation for the client looks really nice. This is elliptic curve Diffie-Hellman here, basically. Private key times G, same on both sides. The server calculation is a little bit more convoluted because this is where we inject that username and password information, given that this is opaque. So we take some concatenation, some hashes, the salt, to get this I value. This I value is input to get a point on the curve gamma, and then the x-coordinate of gamma is used to calculate the public key. We can figure that out. But the important thing is, what is MikroTik doing? And here we have our first concern. So MikroTik is very clearly double hashing this x-coordinate before it plots it on the curve. And because we know that hashes are irreversible, this is concerning because this is going to have knock-on effects that the client has to replicate. So now all of a sudden we should expect differences in the final calculations. And what we see here in orange is that quite a bit is different from the MikroTik calculation versus the draft. I'll admit at this point, I assumed I did multiple things wrong, reviewed the code, and this is in fact how MikroTik calculates from the client's perspective on the left, the server's perspective on the right of the equal sign to share a secret, and it does work, which is pretty remarkable that so many changes can result in a valid cryptographic protocol. So we can revel in this. I certainly did. You can as well. But that's not the goal of our investigation here. We want to be able to authenticate, and there are a couple steps left. So we'll transmit a confirmation code. It'll be the hash of some values to prove that we have the shared secret. And if we have the shared secret that's the same, that is also performed authentication, given that this is opaque. Then we can use that shared secret to initialize AES, CBC keys and IVs, HMAC keys for message authentication, for transferring and receiving. And just when we think we're done, MikroTik throws us one last hurdle, and that's a unique padding for their block cipher, which is almost PKCS7, but not quite. So we'll make that final tweak, and then we'll account for fragmentation of messages that are over 255 bytes long, figure out how to defragment those on the other side, And now we've authenticated and have the ability to send encrypted and decrypted messages back and forth to MikroTik. I think that's pretty cool. You might not think that that's super cool, but you might be interested in using the tools. So if you're one of those people, we have that available to you. Our first repo here has client-side versions of Winbox and Mac Telnet, which is another common MikroTik service. So you can just plug and play those, authenticate, and then start sending messages back and forth. If you're someone that's a little bit more curious, I've also developed a server-side implementation of Winbox. So you can connect the server to the client and watch that authentication progress and watch those messages go back and forth. I've also implemented the IEEE version of the draft submission that's just shown in the second repo here. So you can investigate that and its similarities and differences to the MikroTik version. And then if you're in the third category, which happens to be a cryptographer looking for something to do, what you'll notice is that I have not commented at all on the security of these protocols, because that is well outside of my area of expertise. So it'd be interesting to see someone analyze either the draft or the MikroTik version for security properties, good or otherwise. Because at the end of the day, we're left with one final question, which is why? We have a perfectly good IEEE draft here, albeit old and archived, but MikroTik made all of these changes in order to implement their own protocol. We can only surmise maybe it's they found a cryptographic vulnerability and fixed it in their version. Maybe they hired a team or the individual who made the draft to further obscure this obscure itself protocol to make our reverse engineering harder, in which case mission accomplished. But until we have some more discourse, some more investigation of these protocols, we're just left to wonder why. And given that this is such a prevalent router that's available all over the world, it behooves us again to continue this research and understand if these protocols are in fact secure.
All right, now we're going to get into a RouterOS remote jailbreak that we found. It's a cool ROP chain. All right, so our journey is going to start with the RouterOS HTTP server. So we started looking at this because it has a large surface, it's a huge binary, it's had bugs in the past, so it might be vulnerable still. And yeah, so here's a screenshot of it. I think you've already seen something like this. The core functionality is implemented in Nova bin www. So we can start looking at that, and we see some interesting stuff when we look at main. So straight off the bat, we see these weird function calls. It's doing comparisons to constants. If that fails, it'll try to dereference 0, or it'll exit. Weird stuff like that. We also see this strange function that runs right before main. It's in the init array. It'll do ptrace_me, sort of classic anti-debug trick. It'll very securely construct this proc mem string. Then it'll try to open memory and read memory. Then it gets into some more complicated math. And basically, it'll end up writing values back into process memory so that those conditions that we saw end up passing. So it seems like there's pretty secure anti-debug here. And we can't actually run Nova bin www under GDB, which sucks. But what if we just attach after it starts? And it turns out that this works. So not super secure, pretty easy to bypass. And now we can get into the meat of www. So one of the interesting functions we see that's called pretty early on is this server factory load config function, which presumably loads a configuration file. And it reads another one of those x3 files. So here it's reading nova etc www system.x3. And we can use our same decoder to produce some pseudo XML. We see there's like two main sections. There's www and there's an SSL version. And these seem to be a bunch of, these end up being servlets that are registered to certain URL prefixes. And in particular, if we look at this value here, this indicates the type of the servlet. So we see a lot of servlets that are just dir for directory. This is presumably just like forwarding a directory on the web server. We also see things like index, JS proxy, Winbox, and so on. And these names all correspond to shared object, shared libraries in Nova lib www. So it turns out each servlet sort of implements its own functionality in a separate shared object file. And these files are all shared objects that have the extension .p for some reason I don't know. So when requests come in, the web server will basically look at the first part of the URL and try to figure out which servlet should handle that request. And then it'll, if it finds a servlet, it will forward the request. So in this case, if we send it like /JS proxy, it'll forward that to JS proxy servlet do get or do post, and those functions are all implemented in the shared library for that servlet. So this is like a pretty standard way you would set up a web server with different servlets handling different components. So that's not too surprising. And we see that in the memory map for www, these shared objects get loaded into memory. So that also makes sense. One interesting thing we see is that www actually starts with no servlets active. So it has this configuration list, but it doesn't actually load them until you request something with that URL. So for example, here's a snippet of the logs for www. The first 4 lines are just printed when it starts up. Later on, we try to load /JS proxy, and then we see this message, found servlet, loading, and that indicates that it's loading it. So that's interesting. Additionally, with our message tracer, we saw this kind of weird message happening every time we loaded a servlet. So it's strange because it's sending a message from www to www/2. So why? And also, we see these 2 kind of suspicious values here, which look a lot like virtual addresses. And remember that this is all inter-process communication. So the idea is you're sending messages from one process to another process. So these virtual addresses should be sort of meaningless when you switch processes. So what is happening here? So we can look at www/2. This is the handler that it's invoking. Most of these handlers use the default function, which just does nothing. But we see here that they've implemented command unknown, which will get invoked for commands it doesn't know about. And in this case, it's doing something FOIS handler. So that's interesting. So we can look at FOIS handler, and it's really small. And all it's doing is pulling the value 11 from the message, and then invoking that as a function with 2 other values that it's pulled from the message. So that's pretty weird. So if we can invoke this handler with a message we control, we can just call any pointer with 2 additional pointers that we also control, which is pretty interesting. So it turns out that the MikroTik developers thought it would be a good idea. Basically, when a servlet loads, there's a function that needs to run. So instead of doing something reasonable like having www look up a symbol in the library and calling it, they just have the library send a message to www with the function pointer, and then www will call it. So that's pretty interesting. So can we call this? So as Ian described before, when we authenticate with Winbox, after we reverse engineer the client, we can send arbitrary messages internally. This happens all post-authentication. So for example, here we're trying to send a message to a binary that doesn't exist with hello world, and we see that pop up in our message tracer. Unfortunately, you see there's also a lot of extra fields that are getting appended here because our message is getting proxied through a binary. And there's one that's very frustrating, which is this permission field. So basically, depending on which user you authenticate, they will have different permissions. And this permission is specified in a bit mask, and it gets appended to whatever message we try to send. So if we try to, once we send this message, the target handler will check the permission before invoking the handler code. And if the handler has a policy that doesn't match our permission, it will just reject that message. And unfortunately for us, FOIS handler has this maximum policy of the top bit being set. And this policy is basically only used for like internal services that should only be called by other like internal services. By default, as the admin user, we have this 5FFFE policy, which is sort of the maximum we can get. And if you look on the right, this is what the GUI looks like for setting policies. So each bit in that number corresponds to like one particular function. And unfortunately, with the GUI, we can't actually set this top bit. But the GUI is just, internally, it's sending a message with a bit mask. So what if we just like replace that message with a bit mask with maximum policy? And this works. So we can just set our policy to FFFFFFF. And now we're sort of like, we've upgraded from admin to like super admin. We can call any handler. So here's our hello message. You see hello world, and the permission is hex FFFFF. So now we have all we need for this remote jailbreak. The first thing we're going to do is upload 2 binaries. So we'll upload stage 2, which is just like a shell spawner. We'll upload BusyBox because it's nice to have. We can do this with FTP. You can also do this with the web server. You do need authentication credentials to do this. So it's worth noting that you can upload executables in RouterOS, but they get marked non-executable, and there's actually no default way to run these binaries once they're uploaded. They're just files. So the next thing is we'll upgrade our policy with this vulnerability we found. So we become super admin. Then finally, we can just throw a message at FOIS handler. Our message is on the stack, and since we can just call any function, we can pretty easily set up a ROP chain. It's worth noting, in version 6, there is ASLR, but there's no pi, so we have a lot of gadgets to use. This ROP chain, for example, just marks stage 2 as executable and then invokes it. So it just starts our shell listener running. And then we get remote shell. So once our listener is running, we can connect over port 1337, and it'll spawn BusyBox for us, and then we have remote access. So this jailbreak is done. We're pending release. Hopefully it will be released in a few days, although you probably have enough information from this. If you want to try to do it yourself, it might be a fun exercise. This vulnerability exists in every version 6 RouterOS we could find. So all the way back to 2016, which is the earliest thing we could download from the MikroTik website, and all the way up to the current latest stable and long-term support versions. Unfortunately, www had a huge refactor for version 7, so they entirely removed this FOIS handler and are now doing much more reasonable things with servlets. So it doesn't exist in version 7, but it works on all version 6 RouterOS.
All right, so we threw quite a bit of information at you, so it bears at least a small recap. So again, the purpose of this talk was to provide information and tools to you so that you can dive into MikroTik however you're interested. The knowledge we covered is we talked about what MikroTik packages look like, how they're cryptographically signed, and then how to bypass that cryptographic signature to patch your own firmware. We dove into the message protocol, how that's used, and we showed some live demos of that being run. And then talked about message routing, so you can kind of understand from a system-wide implementation how these routers function. We talked about authentication, gave you the tools you need to authenticate to the bypassing this ECSRP protocol, and then finally released our novel jailbreak. So now you have the tools and knowledge available so that you can dive in, because at the end of the day, this is a company that prefers to obscure what they do. It definitely doesn't live in the public light, and it's up to us as researchers to drag them back into that limelight. So with that, thank you for listening, and we'll open it up to questions. Yeah.
Bear with me, if you will. It's late in the day, and I'm kind of tired.
Yes, sir.
I wanted to summarize the mistakes they made at a high level. So there's a backdoor because of the devel login. The signature was based on size instead of cryptographic hashing. Is that what I understood?
Are you referring to the package signature?
Yeah.
Yeah, so the package signature, as far as we know, is pretty legit. Basically, we just patched the firmware directly to remove signature validation, which is something you can only do if you have access to the firmware.
And then they hand-rolled the crypto while not being a cryptographer, right?
Sorry, can you repeat?
Hand-rolled the crypto, yep.
Yeah.
They enabled GDB with minus attach. The voice handler sends a raw address instead of validating a lookup. They had an unprotected policy bits. What did I miss?
That sounds pretty good. Sounds pretty comprehensive.
That's most of it.
All right, thanks.
I'm assuming when you first started looking at the router itself, you most likely ran an Nmap scan. Aside from port 80, were there any other externally exposed ports?
Sorry, I couldn't understand the question. Could you speak up?
When you guys first started looking at the router, I'm assuming you ran an Nmap scanner just to see what was open. Aside from port 80 or whichever port the web UI is fronted on, is there anything that's noticeable that's open, like an FTP server or something like that?
Yeah, there are a few other services running. So I think by default they have Telnet, SSH, FTP, sort of standard things.
They have their kind of proprietary services as well. So Winbox, that GUI is automatically exposed. Mac Telnet, which I referenced, is just another way of getting kind of a shell. They give you scripts to basically implement your own Mac Telnet client. So yeah, they do have a variety of services exposed.
Did you see how they were using the FOIS handler for other legitimate purposes?
Yeah, so
Or were they?
what they were trying to do was basically when they load a servlet, they need to invoke a function in the servlet to like register it with www binary. And so for whatever reason, they thought it was a good idea to use inter-process communication rather than like inside the process communication.
When you patched the init.rd, how did you actually get that back on the device? Did you already have file system access, or how did that take place?
Yeah, so we were doing most of our research with the virtual image, so we're running it like in VirtualBox, so we just have access directly to the disk image. Not super familiar with the actual device. I know you can reflash certain parts if you have like physical access, but that's not something we looked into in great detail.
Okay, thank you.
All right. Thank you. So, just a question?
For your compression matching, did you use a tool, or did you write a tool for that? And did you do the math for the compression, or did you just kind of keep upping the entropy until it matched?
Yeah, for compression matching, I wrote a bash script to do a binary search on the ratio of 0 to dev random that we're writing into pad. It's not super complicated. Basically, as long as you get the maximum compression size and the minimum compression size outside of your target compression size, then you're able to do this.
All right. Thank you all.